together, and to thank all of you for coming here. And also, of course, I would like to thank the IIP for again financing such a nice workshop and for the hospitality here. So it's always nice to come here to Natal. And maybe next I should also start with an apology for organizing a workshop on transport and then talking about something that is not really that closely related to transport. My apology for that is that I wasn't really planning to give a talk here, so it was more sort of short notice. And Andreas Klümper has already talked on Wednesday on about one of our projects which are more closely related to transport. Okay, so that's should be enough with apologies. So let's go ahead. So what I want to talk about here today is what has been or become known as dynamical phase transitions, sort of related to pointer. Here. So which is based here on this Loschmidt echo. And in my talk, so first of all, I want to go back to something we did a sort of few years back, and showing that although it's sort of become known as dynamical phase transitions, maybe one shouldn't put too much emphasis on them. So there is one can show that there is not necessarily a connection between these dynamical phase transitions and equilibrium phase transitions. So I just want to remind you of that first. But then I just want to go ahead and take a pragmatical point of view. So this is an interesting sort of non-equilibrium quantity one can study. It's a quantity which in principle is measurable in experiment and which can give us some information about the non-equilibrium dynamics of a, say, strongly correlated system. So the general idea of the Loschmidt echo is the following. So we have an initial state here, and then we time evolve it with some Hamiltonian forward in time, and then we imagine that this Hamiltonian is slightly changed, and we evolve backward in time and ask sort of how large the overlap is after a given time t. And here I want to make one further simplification. So I want to assume that this state psi0 is actually the ground, or is an eigenstate of the Hamiltonian H0, so that the Loschmidt echo can be written in this form here. So we have this initial state, this eigenstate of this Hamiltonian. We time evolve it with some Hamiltonian and then ask for the overlap. And written in this form, it becomes clear that the Loschmidt echo is nothing but a time-dependent fidelity. Yeah? So it asks, as a function of time, how large the overlap between these two states is. Okay, then one more general comment I want to make. I mean, it's easy by introducing sort of an eigenbasis here to calculate the average, say for finite Hilbert space, and assuming no degeneracies. And one then sees that this average Loschmidt echo is given by matrix elements overlaps between the state psi0 and all the eigenstates of this Hamiltonian H. So in particular, it is obviously not just the overlap between the initial and final ground states. Okay, then if we apply this formalism to a many body system, then we typically expect that the overlap between such states will be exponentially small in system size. So if they're not parallel, and so it makes sense to define a return rate in the following way. So we take the logarithm of this Loschmidt echo and divide by 1 over n, and we're interested in this quantity in the thermodynamic limit system size n to infinity. And here I will sort of study only sort of one-dimensional, so linear systems. Okay, and this form here of the return rate that sort of looks sort of enticing, looks very suggestive, because it has exactly the form of a thermodynamic potential. And we know that if we take a real thermodynamic potential, then sort of non-analyticities in that potential can tell us about phases and phase transitions in the model. So that has sort of motivated these questions if one can maybe look at this quantity here as telling us something about phase transitions, dynamical phase transitions in time, and how, if they exist, how they are related to equilibrium phase transitions. Okay, so how does this analogy work in detail? So we can consider this quantity here as a partition function, but rather instead of taking the trace as we're used to in thermodynamics, we have sort of fixed boundaries here. So we have sort of like a partition function, but the boundaries are fixed. And now instead of just considering sort of real time here, I allow IT to be a general sort of complex number. And then the thermodynamic potential in the usual way can be defined as by the logarithm of this partition function. And the return rate we get back to if we set z equal to IT and take the sum of fit and the complex conjugate. Okay, and then the idea was to understand non-analyticities in L of t by investigating zeros of this partition function in the complex plane. And again, this follows really closely what has been done many decades back in the thermodynamic case. So just as a reminder, if we have a thermodynamic partition function, then there is this notion of Liang zeros. If we look at the grand canonical partition function and we introduce a complex fugacity, and these are very well understood because in that case the partition function is sort of polynomial in this fugacity. There's also another way to do that so this is sort of the grand canonical description. One can do something similar also in the canonical description, which are then called sort of the Fisher zeros. So one looks at the canonical partition function and introduces a complex inverse temperature beta, and these Fisher zeros often have a very complicated structure, whereas much more is known and the structure is often much simpler for these Liang zeros. So this here is more in the class of these Fisher zeros, with the difference that we have these fixed boundaries. Okay, so then there comes sort of the first caveat here. So if we look at the usual thermodynamic partition function, then these are positive definite analytic functions for finite systems. So there are no zeros on the real axis. So zeros can or non-analyticities in the thermodynamic potential can only show up in the thermodynamic limit, and this happens if zeros accumulate near the real axis, and this is sort of a tracer where phase transitions will occur if we perform the thermodynamic limit. On the other hand, if we have this partition function here with the fixed boundaries, so we look at this here, then obviously we can have zeros for times Tc already for finite systems, so there's nothing which forbids that. And also this these zeros, I mean this set of z is not a simple polynomial in z, so we expect these zeros, I mean they can be everywhere, and the structure is also certainly expected to be quite complicated in general. Let me also explain to you a little bit in sort of in a more graphical language how these two partition functions look like, and also how one can calculate them in principle numerically, say in the thermodynamic limit for a one-dimensional system. So I show here the partition function essentially for a thermodynamic system. So we have a system with periodicity in inverse temperature beta, and I also assume periodic boundary conditions along the spatial direction, so we end up with a torus geometry. For this torus, we can define a quantum transfer matrix in the usual way, and from this quantum transfer matrix, from the eigenvalues of this quantum transfer matrix, we can determine the thermodynamics of the system. Now, if we compare this to this Low-Schmidt amplitude, this generalized Low-Schmidt amplitude, then the geometry is now the geometry of a cylinder, so we have still periodic boundary conditions in space, but in the z direction here, we have fixed boundaries, and these boundaries are fixed by the initial state, psi 0. But again, we can define a transfer matrix for this cylinder here, and by determining the eigenvalues of this transfer matrix, we're able sort of to map out the Fisher zeros of this partition function here. Okay, and to be more explicit, so the idea is to do a Trotter-Suzuki decomposition for this partition function, define a transfer matrix which is traced along the spatial direction. M is the Trotter-Suzuki parameter which we want to send to infinity at the end, with Z, or this what I called so this Z, so essentially being split into small pieces, Z over M. And then this quantum transfer matrix consists of these sort of plaquettes, which you see here, these ones here, which I called T bar. And there are two special ones which sit here at the lower and upper end, and these special ones have sort of one side of the plaquette is sort of fixed by the initial condition. So we have these modified boundary weights. And then, as in the thermodynamic case, we can calculate this thermodynamic potential by simply determining the largest eigenvalue of this transfer matrix. So if we know the largest eigenvalue of the transfer matrix, this gives us the thermodynamic potential. If we want to look for Fisher zeros, then those occur if the leading eigenvalue crosses with one of the next leading eigenvalues of this transfer matrix. And this can be understood as a divergence of a correlation length. So in general, in this transfer matrix formalism, correlation lengths are given by ratios of the leading to next leading eigenvalues. And in the thermodynamic case, in one dimension, we know there are no phase transitions at finite temperature, so this ratio here, there's always a gap between the leading and next leading eigenvalues. That's no longer true here, so in this case, such crossings can occur, and by mapping these crossings, we can find the Fisher zeros. And the test case, which has been used in the past, is the Transverse Isaac model. In this case, one can show that non-analyticities in this return rate only appear if one quenches across a critical point. So for the Isaac model, there is indeed a direct one-to-one correspondence between these dynamical phase transitions and equilibrium phase transitions. And here I show you how these Fisher zeros look like in the complex plane. So my parameter Z is IT plus some R, and the points where sort of this Low-Schmidt amplitude becomes 0 are then the points where these Fisher zeros cross this line R equals 0 here. So and you see they fall onto some lines which one can follow. These blue lines are analytically calculated, and these dots I'm showing here are calculating by using DMRG to diagonalize the transfer matrix. Okay, so the advantage of using sort of DMRG numerics for this transfer matrix is then, of course, that one can go beyond the Transverse Isaac model and look at more sort of complicated interacting models. And here in particular, we had looked at the XXZ model, and in this case, actually, things become more complicated. So, for example, one can immediately understand that not every quench across a phase transition has to lead to singularities. Obviously, if I choose psi 0 as the ferromagnetic state, then the quench will not change this partition function. Also, the total magnetization is conserved. That means quenches in the magnetization also will not lead to any dynamics. However, one can also find sort of cases numerically where L of t has some non-trivial dynamics, but still where this holds, so where one crosses a phase transition in the known phase diagram without any non-analyticities in L of t. Yeah, so in this case, there is no longer this one-to-one correspondence, which people got excited about in the Isaac model. So here in this case, this no longer holds. And the opposite actually is also true. One can construct examples in this model for quenches where one stays in the same phase. So I'll just show you one example for a quench from some large value of delta close to the transition line at delta equal to 1. And what I'm plotting here, these lines are the leading eigenvalues of the transfer matrix as a function of time. So at the beginning, as you see, this is the leading one, and then there is one coming down, and which crosses here and here and here. So there are non-analyticities if you just follow the leading eigenvalue in this return rate. And same is also shown here in this example. So you can see it here in the inset, maybe better. So there is this next leading eigenvalue which crosses over here, and this leads to these cusps here in the return rate. Okay, so this is what we did sort of a while ago. Let me, as I said, now take sort of a pragmatic approach and look what we can learn in case of special models. And the ones I want to discuss here are models which have these symmetry protected topological phases, so in one dimension, so Gaussian models, which I can write in the following form. So it's a free model, so can I write the Hamiltonian in this way, and I have a vector D here multiplied by the vector of Pauli matrices. And these Pauli matrices, they act in some subspace, which could be either particle hole subspace or could also be a subspace inside a unit cell. And for this case, one can calculate the Low-Schmidt amplitude analytically. It has been done a while ago back already. So in this case, this Low-Schmidt amplitude is given by this expression here, where these d hat vectors are just these d vectors from the Hamiltonian before the quench, which I denote by 0, and after the quench denoted by 1, normalized by this expression here. Okay, so now one can ask, okay, when does this quantity here become 0? And one sees that that happens in the complex plane for these values here of time. And in particular, we find non-analytic behavior in the return rate if the imaginary part here vanishes, which happens if we can find a momentum k star for which this product here is 0. If that's the case, then these critical times are given by this expression here. So where this here is the energy at this momentum k star of the post-quench Hamiltonian. Okay, and if one does that here in these SPT models, one can actually show if one quenches from one topological phase to another, then it's sort of guaranteed that there is such a momentum k star where this condition here is fulfilled. So at least in one direction now one has something which one likes. So if one crosses a topological phase transition, there is a non-analyticity in this quantity. However, that still does not exclude, and one can construct examples where that happens, that such phase transitions occur if one stays in the same phase. So now what we wanted to do here, I mean the first sort of recent work I want to show you is we wanted to look at sort of boundary contributions to this Low-Schmidt echo. So you know that in general there is a bulk boundary correspondence in these topological systems. So if one is in a topological phase, one typically has edge states. And the question we were asking here is, can these dynamical phase transitions be understood as periodic transitions between trivial and non-trivial phases, and are there related boundary contributions to the Low-Schmidt echo? And to do that, we can no longer sort of simply calculate the Low-Schmidt echo analytically. So this analytic solution here, of course, was based on the fact that momentum is a good quantum number before and after the quench. If we now want to do the same thing for an open system, that's no longer the case, so we have to do it differently. And for a Gaussian model, for a free model, there is a simple formula to calculate this Low-Schmidt echo, which is sort of a determinant of a quantity here, which depends on the single particle correlation matrix only. Yeah, so one has to calculate the single particle correlation matrix. This is a time evolution operator, and then taking this determinant, one gets the Low-Schmidt echo. And what we did here is sort of two different ways to look at these boundary contributions. So one way is just doing this program here for larger and larger systems, doing a finite size scaling and extracting the boundary contribution. And then I want to show you that what we find there is actually related directly to the eigenvalues of this matrix M here. So this is this dynamical matrix M. Okay, let me now use a concrete example for such a model. So just you get this SSH model. So this is a model where the hopping amplitude is modulated from 1 plus delta to 1 minus delta, moving along the chain. And what I want to consider are symmetric quenches, so going from minus delta to delta or vice versa. And for the bulk contribution, one can show that the quench direction actually does not matter. So for the symmetric quenches, it does not matter in which direction one goes. And so this is how the return rate looks like for delta quite large, close to 1, where these sort of dimers are almost decoupled. And this is for some smaller delta value. Now what happens to the boundary contribution? So in the boundary contribution now actually does play a role if one quenches from the trivial phase to the topological phase, or if one quenches from the topological to the trivial phase. And in particular, if one starts out in the trivial phase and quenches to the topological phase, then this boundary contribution actually shows an interesting behavior. So it's 0 or essentially 0 over here, and then right at the critical time it jumps up to some finite value, then jumps down again and jumps up again. Yeah, so there is really like a periodic transition where this boundary contribution shows up and then disappears again. And this is very different from doing the quench the other direction, from the topological to the trivial phase. So in this case, the boundary contribution is always very, very small and shows some kind of divergence near the, or kind of, it's numerically hard to resolve, so it goes up here near the critical times Tc. But the scale, as you can see here, is orders of magnitude smaller than doing the quench in the opposite direction. So now one can ask, where does this come from? Why is there such a boundary contribution? And to understand that, it is helpful to look back at this dynamical matrix M here. So we need to calculate the determinant of that, so it makes sense to look at the eigenvalues of this matrix. And this is what's plotted here. So if we take this matrix and we look at the eigenvalues, so this is now this quench here from the trivial to the topological phase. These black dots here are the eigenvalues of this matrix for a finite system. The green ones are the argument. And you can see there is something interesting happening. So if one reaches the critical time, there is a pair of eigenvalues which comes down and stays 0 up to the next critical time, and then sort of joins the other eigenvalues, comes down again, and is 0 over here. And if one just takes a contribution of these two eigenvalues to the Low-Schmidt amplitude, then this actually exactly reproduces this boundary contribution. So the boundary contribution which one sees in this case is indeed almost entirely due to this pair of eigenvalues which sit here at 0 energy. And this is not specific for this SSH model. One can also look at other models and similar quenches, say models with more edge states, and one gets a similar picture there as well. Okay, there's also something interesting going on in these quenches in the entanglement entropy. So if one quenches, for example, from the trivial to the topological phase, I show here some large value of delta. There's a similar picture for smaller delta, but this is sort of the most clear. Then one starts here at 0 entropy, goes, or almost 0 entropy, goes up, and sees these oscillations here, and these oscillations go up to 2 log 2 for a long time, and then at even longer times one sees some linear increase, but on top of this linear increase there are still oscillations, and these oscillations, these local extrema, actually occur again at the critical times Tc. So these critical times Tc, where one sees these cusps in the return rate, they also show up here in the entanglement entropy. And well, again, one can ask where that comes from. So let me show you the correlations in this system. So at time equal to 0, we start out in the trivial phase. So we mostly have correlations between these nearest neighbors, so these dimers you're forming, there are also correlations between, so this is a true ground state, and these are the single particle correlations. Now, if we quench the system, it actually goes through an interesting evolution, so at times Tc, instead of now having the strongest correlations between nearest neighbors, we now have the strongest correlations between next nearest neighbors. So one gets this structure here. And we cut the system here in the middle, so if we cut at time equals 0, the entropy is almost 0, so there's a little bit of correlations here, but it's close to 0. Whereas if we cut at time Tc, you see we cut 2 of these correlations here, and each one of them essentially contributes log 2 in this case, so we get this 2 log 2 behavior. And then if you go to 2Tc, we essentially we go back to a state which looks very similar to this one, and then we move on and get again this state here. Of course, over time, there will be sort of correlations sort of building up here, and once this happens, then one sees this linear increase which sets in at longer times. Okay, if one does the quench in the opposite direction, that's actually also quite interesting. So here we start out in the topological phase against for large delta. So now one has these dimers, sort of one removed from the edge, and one has these edges of the chain which are actually strongly correlated. So these are these edge states. One has this symmetric antisymmetric combination, and therefore there is a strong correlation between these edges here. And at time t equal to 0, if we cut through here, we get sort of 2 log 2. If you go to time Tc, there is still this long-range correlation, but now instead of connecting the 2 edges, it connects the sides which are one removed from the edge. So it moves over here. But now you see, in this case, the entanglement entropy will not show these strong oscillations, because in this case, the entanglement entropy is also close to 2 log 2. And then it goes back to this state again and up to this one here. So there are these sort of oscillations also in the correlations with this time scale Tc. Okay, then so this was one part what we did recently. Then let me tell you about the other project we did, which sort of was generalizing the whole thing to density matrices. So far I've looked at this Low-Schmidt amplitude for pure states. And one way to look at this is as the Low-Schmidt echo as defining essentially a metric in Hilbert space. So if one takes the absolute value and, for example, takes the Jacobs cosine of that, one can use this as a metric. So if the states are the same, then one gets 0 here, and if they're orthogonal, one goes to sort of pi over 2. So this can be shown to fulfill all the criteria for a metric. And now the question is, if one wants to generalize to density matrices, what does one sort of demand? So, and that is not necessarily unique. So, I mean, one can look, maybe take some ideas from experiments, what could possibly be measured, or one can maybe take a more sort of mathematical perspective. Let me show you first what happens if one demands that one generalizes this notion of a metric to density matrices. So then what we would like to have are the following properties. So we want to introduce a Low-Schmidt echo, which is now a function of 2 density matrices, one at time equals 0, one at time equal to t. We want to have the absolute value between 0 and 1. We want this Low-Schmidt echo to be 1 if these 2 density matrices are identical. And I mean, at the beginning, and also if they are identical at later time, only then should this be 1. And of course, this should also be symmetric. So if I exchange these 2 density matrices, that shouldn't change the Low-Schmidt echo. And if one demands these things, then this is very well known, has been done sort of already in the 60s and 70s for density matrix without the time dependence, but one can directly of course, also add the time dependence. So in this case, one can define the Low-Schmidt echo as a trace of this complicated object here, and one can show that this indeed fulfills all these properties which are needed to define a matrix. And in particular, if one takes temperature to 0, then this quantity indeed becomes this Low-Schmidt echo here, so the absolute value of this expression, if this rho of 0 is a thermal density matrix. So this is one way to do it. Another way, which may be more sort of motivated by experiments, is the following. Let's imagine we prepare our system in some mixed state, and then we can do some projective measurements. So after some time t, we can sort of project that state onto a pure state and measure this overlap. Then perhaps we can define a Low-Schmidt echo in this way, where I introduce sort of a normalization factor so that it's equal to 1 at time equal to 0. So this is one way, and related measurements have been done sort of last year in trapped ions. There are also other sort of unrelated generalizations which have been given in the literature. One is sort of taking the trace of the density matrix with the time evolution operator. Here, if one introduces a eigenbasis, one sees that this here is actually something like an average over Low-Schmidt echoes in the excited states, and not really a generalization to density matrices. In particular, this quantity looks sort of a bit boring, because one can already see that there will never be any zeros, because you have to do a lot of fine-tuning to have all these coefficients to become 0 at the same time. Yeah, so which would mean that there is some time where all these eigenstates become orthogonal after some time t. And the same has been also done for if one starts in particular with a canonical density matrix as initial condition. And again, this turns into some average of Low-Schmidt echoes with these weights Pn, now given just by the sort of canonical weights. Okay, so I want to I'm not going to talk any further about these two here. So I want to concentrate on this definition here, and also look at this projective one. Okay, and the results are again for Gaussian models, because then we can calculate things analytically. If we do, in this case, a projection onto a pure state and starting from a thermal density matrix, one can derive an analytic result where this theta here is the Bogoliubov angle between the sort of operators which diagonalize the Hamiltonian before and after the quench. And from this result, one immediately sees that zeros are only possible at temperature T equals 0. So what I need is that this factor here in brackets is equal to 1, and this only happens for beta to infinity. Yeah, so once you have finite temperatures, there will be no zeros anymore in this Low-Schmidt echo. The same similar calculation can also be done for this object here, which is always a bit nasty, and I have no idea how to do this numerically, but for these sort of free models, one can do it analytically. And this is the result here. So it's a product over k, and then one has this expression here. And what shows up in here is just the sort of Low-Schmidt echo for the pure state and with momentum k. And again, one sees that this expression here will always be larger than 0 for any finite temperature t. So only for beta to infinity does this reduce again to the 0 temperature Low-Schmidt echo. So any finite temperature essentially washes out the singularities in the return rate. And this can be seen here in this example. So I use again the Ising model, plot the return rate at 0 temperature. This is the first kink which shows up at time Tc. And if one increases sort of temperature, then this kink here sort of gets essentially immediately washed out. This here is for the projective measurements. So this is this result here. And the second one here is for this generalized Low-Schmidt echo based on this metric in the space of density matrices. And the same thing is true. So once one introduces finite temperature, these singularities are going to get washed out. Okay, and then finally, I want to take this whole approach and also apply it to open systems. So for open systems, our density matrix no longer just evolves under this sort of unitary part, but there are also in addition, there's also an addition and dissipative part, and here, which is given by this part here. And here in particular, I want to consider again these Gaussian models, so these kind of models here. And as a dissipator, I consider particle loss and particle creation. Yeah? So there are reservoirs which each of them couples only to one K mode, and there can be either particles being taken out or particles added. And for a quench in the Ising model, say where we only have particle loss, we get this analytical result here, where this capital gamma is defined as the loss rate for the modes with wave vector k, plus or minus the loss rate for the particles with minus k. And again, if one looks at this here a bit more closely, one finds that there are no dynamical phase transitions, so no zeros if one has a finite loss rate. And instead of staring at this equation, I'll just show you the plot. So this is the return rate here, again shown as a function of time, plotted as t over tc. If there is no loss, you see these cusps here showing up again with this spacing tc. Now if you add a loss rate, then this return rate goes up here actually to some sort of universal value at long times, which is independent of the loss rate and only depends on the initial and the final Hamiltonian. And if one looks, sort of zooms in more closely here at this first cusp, one sees that this first cusp here, actually up here, gets washed out again very quickly. So once there is particle loss, this cusp disappears very quickly for already extremely small loss rates. Okay, so then the question, last question I want to ask is, I mean, if we have an open system, then often we have the possibility to fine-tune. So we say if you think about a cavity or something, one can tune maybe loss rate, and can think maybe also sort of playing around with this a little bit. So the question is, can we do some sort of fine-tuning so that such zeros still occur although the system is open? And this is just sort of a proof of principle example, maybe not very physically relevant. So I look at this system now which has an annihilation rate for particles with momentum k, and also particle creation with this rate gamma bar for particles minus k. And then I get this expression here. And if we do some fine-tuning here, where we have an equal creation and loss rate, so the creation rate for particles with minus k is the same as the loss rate for particles with momentum k, then one can actually simplify this expression and finds that this Low-Schmidt echo, this is sort of the generalized metric one for density matrices, looks like the pure state one with an additional exponential decay factor in here. And if one takes the logarithm of this, then one finds for the Low-Schmidt echo the same as, for the return rate, the same as for the pure state, but there is an additional sort of linear increase in here. So if one plots this, it looks as follows. So without particle loss and creation, this is the result again for the Ising chain. And if I turn on this fine-tuned loss and creation, then I get this additional sort of linear increase, but you can see that these cusps here still survive. Yeah, so in principle, one can do some fine-tuning where these non-analyticities survive in an open system. Okay, that brings me to my conclusions. So I showed you some sort of results, study of these sort of Fisher zeros in this generalized partition function. So this looks like partition functions in the thermodynamic case, but now with sort of fixed boundaries at the ends, and sort of studies of these related non-analyticities in the return rate, if we set this parameter z here to it, so if we look at real times. And I showed you that this partition function can be in general calculated from a transfer matrix with fixed boundaries, and by using this method to study several models like the XXZ model, we can say that in general the non-analyticities in the return rate are not related to equilibrium phase transitions. Yeah, so in that sense, maybe this whole idea, after all, is not that exciting because there is in general no direct relation to equilibrium phase transition. Nevertheless, it's an interesting sort of dynamical quantity, which is also possibly can be measured. So there is some interest in understanding sort of how it behaves and how it can be also generalized. And so I showed you generalizations to density matrices, either by demanding that it can still serve to define a metric in the space of density matrices, or by this idea of a projection after time evolution onto a pure state. And in both cases, if one introduces in particular finite temperatures, so if one looks at thermal density matrices, then any finite temperature washes out non-analyticities. And the same is also true for generic dissipation. So if one looks at open systems, then typically also they immediately disappear. but in this case, if one has sort of control over the system, fine-tuning is in principle possible so that they also survive in a case with dissipation. Okay, and then for these SPT models, I had sort of some specific results which were related to boundary contributions, which I found quite interesting. So there are also in this Low-Schmidt echo, one can see the contribution from the edge states in the 1/n corrections and to the Low-Schmidt echo, and they are actually related to these eigenvalues in the Low-Schmidt echo matrix, which show these sort of time periodic sort of zero modes, so two eigenvalues which go to zero with period Tc. And if one looks at the edge correlations, then one sees that even after a large quench, these edge correlations can persist, and they show a Tc periodicity, and this periodicity in these edge correlations then also shows up in the entanglement entropy if one separates the system into two halves. Okay, so that's all I have to say, so thank you for your attention.